Thank you very much. It's a pleasure to give a talk here. So today I will be talking about some sort of counting problems. So let me just briefly, maybe not all of you familiar with the counting type of problems in extreme combinatorics. So I give you a little bit flavor of what kind of problems we're looking at. So counting type problems. The general setup is very simple. Yeah. So the general setup we often given family C is a family of discrete objects. Could be graphs, could be things like this. So it's a family of discrete objects. Oftentimes it comes with certain properties. Certain property. Okay, so the problem we're interested in, oftentimes in this area, there are two problems we can look at. The first problem is to estimate the size of this family. Okay, what is the cardinality of this family to give an estimate? Once you have the estimate, then if you want to look further in, then you want to say something about the structure of the objects in this family. So oftentimes we would like to look at the so-called typical structure. Okay? Typical structure. Yeah. So what do I mean by typical? So basically we know this family, the objects in this family has some property. Now we want to basically use another concise concise way to describe most of the objects in this family. Okay, I'll give you an example. So such kind of problems show up in many different areas. For example, such problems in, for example, extreme graph theory and additive number theory. And some others. Okay, so some examples. In graphs, Erdős, Kleiman, and Rothschild from the 70s, they consider the family C, which is the triangle-free graphs on the fixed vertex set 1 to n. So they consider C in this case is all so I will use bracket n to denote the first n integers. So this is labeled graphs, and the property of this family is that we do not contain a clique of order 3 as subgraph. Okay? So for the first question, they answer both of these two questions. Oftentimes, I want to say that the second question, if you know the typical structure, you oftentimes get a much more precise estimate. Okay? I will tell you what it means later. So for the first question, they prove that, okay, so how can you get a triangle-free graph? Well, the easy way is this two-round graph on two parts is triangle-free. Then any subgraph of it is also, of course, triangle-free. By taking all possible subgraphs, you generate 2 to the n squared over 4 subgraphs. Yeah. So what they prove is this simple trivial lower bound is not too far from the truth. Okay. So for the first, they show that this family C, the family of all triangle-free graphs on vertex set n, is 2 to the n squared over 4 plus a lower order term. Okay, so this is trivial lower bound by taking all possible subgraph is in a sense tight. But of course, this exponential arrow is rather big. It could be, if you move it down here, it could be anything, right? Sub exponential. So for the second question, they actually managed to prove that they prove the typical structure. What did they prove? Almost all such graphs are bipartite. Okay? So what do I mean? Not all triangle-free graphs are bipartite. For example, I can take a blow-up of a C5. This graph has n squared over 5 edges. By taking all possible subgraphs, you generate exponentially many triangle-free graphs, most of which is not bipartite. But they prove that this kind of graph, they are lower order term. There are very, very few of them. In other words, if in C, you put a uniform measure and you draw a graph according to a uniform measure, with probability tending to 1 as n tends to infinity, you will see a bipartite graph. Okay? So this is one of the earliest results.
Doesn't Q1 imply Q2? In this case,
oftentimes Q2 implies Q1 because Q1, this error term in the power is rather big. Yeah. So, and if you know the typical structure, you can enumerate it asymptotically with the error term down here rather than in the power. Yeah. We will see more example of such kind. So since this paper, there are many, many extensions where instead of consider, say, triangle free, it was generalized to larger cliques, for example. Okay. By a paper of, I think it's Rothschild, some people, I don't quite remember. So then we did the extension with Bollock, me, independently by Bouchard, Morris, and Nettle. So basically, we extend the larger clique result to forbidden subgraphs where the order of the subgraph can grow with the ground set of the vertex set. So here we should interpret this forbidden subgraph as a fixed size graph where n tends to infinity. So what we prove is if you look at C to be the family of all kt plus 1 free graphs on n, where t is allowed to be taken to go up to log n to the some power. Okay, t is allowed to grow with n, and we show that we basically solved both problems. So for the stronger result, for the second question, we show that almost all of them are t-partite. Okay, so it's an extension of this result. Right, and there are also generalizations to hypergraphs, to directed graphs. So I want to mention one of such generalization is the induced version. So similarly, you can ask if you forbid a graph as an induced subgraph, what can you say? Yeah. So one such example is, so if you look at the family of all graphs that is induced C2T free, say, does not contain an even cycle, where t is at least 6 for a longer even cycle, then this was solved for the typical structure. This is by Jae Hoon, who's here today, and Kuhn and Ostis from Birmingham, and Townsend, one of their students. Well,
so is it t fixed, or is it like you're forbidding all induced even cycles of lengths and means?
For fixed t, and the ground set for the vertex is growing. Yes, for fixed t. So roughly they show that almost all such graph looks like the following. You have t minus 1 parts. Yeah, in total t minus 1 part. Where the first part is the complement of stars and the strong union of stars and triangles, and the other parts are complete. And in between different parts, you can put whatever edges you want. Okay, so this is the typical structure. All right, so for the graphs, I want to mention one more question. It's another extension of this result. So Erdős asked in the late 80s that rather than looking at all the triangle-free graphs, then what if we look at those that are maximal, in a sense that under graph inclusion, meaning so. Okay, so what is C prime? C prime is a subfamily of C, which is all the maximal triangle-free graphs. Meaning that if you add any edge from the complement, you will create a triangle in a graph. Is that clear, the definition? Yeah, so clearly this subfamily should be smaller, but how much smaller? So he asked for estimate. Like for example, is it exponentially smaller, or is it just about the same, or most of them are maximal? So here's the well, from this result we know there's upper bound is 2 to the n squared over 4. Yeah, there's upper bound. For the lower bound, I can give you 2 to the n squared over 8. How can we generate this many maximal triangle-free graphs? What you do is you split the vertex into 2 equal parts. Okay. Inside, you leave the right-hand side independent. We don't add any edges there. We leave it empty. For the other side, suppose n is divisible by 4. So I put a perfect matching here. Okay. Now, for every pair of edge from the right-hand side and the vertex from the left-hand side and the vertex from the right-hand side, we put exactly one of these edge. Okay, for every pair. For example, here I choose the second edge. You do this. Now, how many such pairs? The number of such pairs is exactly 2 to the n squared over 8. N squared over 8, right? So for each such pair, we have 2 choices. Then in this way, clearly we don't create any triangle. Such graph might not be maximal triangle-free, but you can add some edges inside. They will extend to different maximal triangle-free graphs because they can be distinguished by looking at this cut. Okay, the cut is unique. Okay, so there's this exponential gap here. Then recently, Warwick and Petrichkova showed that in 2015, they proved that they answered the first question basically. They show that this is 2 to the n squared over 8 plus little o n squared. Okay, so the constant 1 over 8 in the power is optimal. This is what they prove. But the much harder question is, how do they look like? Question 2. So this is what we did. This is also with Warwick. So we proved that if you uniformly at random pick a graph from this family C prime, almost all of them look like these. What do I mean by that? Typical structure. Almost all of them looks like those that come from this lower bound construction. Meaning that if you pick a graph with probability tending to 1, you can split the vertex into half, roughly same size, such that on one side you see an independent set, on the other side you see a perfect matching. Okay, this is what we prove. And if you know there's such a cut, then for sure every such pair cross you have to have exactly one edge because this is maximal triangle free. So this is precisely what's coming from this lower bound construction. Yeah.
Are you sure that one side is independent, or
yeah? no edges at all. Yes, this is what we prove. So precisely look like the lower bound construction. Right. So much for the graphs. There are many others. So I will skip those. So maybe a little bit more counting problems in other settings. There's a way to.
One question that
Yeah.
So there's some probability that on the right hand side you might have two vertices sharing, not sharing some vertex on the left. Then you should give.
Here, this.
Yeah, if you have two vertices on the right hand side without having common neighbor on the left hand side, then
it's possible. Yes.
Then you need to add an edge between them to make it maximal.
Yes. So not all such graphs that I describe are maximal. You might have to add some edges inside.
Right.
Okay. But such graphs, they are lower order term.
Right.
That's why we consider the typical structure. Yeah. You're right.
So the probability of having that is
tends to 0. Yeah. They are small, very tiny portion. Yes. Right. So other type of results. I have an hour. Yeah, 50 minutes. Okay. So other types. Let me give you in a different setting, not in graphs. For example, one of the fundamental theorem in extremal set theory is Ehrlich-Corrado. Okay, proving 71, I think, 71. So what did they prove? 61. 60s. So there's this notion of intersecting family. Okay, so a family, suppose we consider, so this is the power set of n. This is all the union of all subset of 1 to n. If you take a family of subset of n, then this family is called intersecting if any two members in the set in this family, they have non-empty intersection. Yeah, they overlap somewhere. Okay, so Ehrlich-Corrado basically shows the maximum size of uniform family that is intersecting. So they prove, Ehrlich-Corrado proved that for any f, that is a subset of, let me write it like this. Okay, this means all k, the right hand side is all k subset of n. So if this is intersecting, then the size of this family is at most m minus 1 choose k minus 1. You cannot go bigger than that. If you go bigger than that, you for sure will see the pair that are disjoint. They don't overlap. Is it? Yeah? So this bound is sharp, easily can be witnessed by this trivial family. Sometimes people call it star. You can grab a special guy, say 1, and you take all possible k sets containing it. Clearly, they're m minus 1 choose k minus 1. Okay, so based on what we have seen so far, you see, you take a maximum size triangle free graph, which has n squared over 4 edges, and you take any possible subgraph of it, you generate 2 to the n squared over 4. Now, there's a very natural question is, do you have 2 to the, say, n minus 1 choose k minus 1? So question 1, if you consider what is the number of k systems or k uniform hypergraphs that intersecting hypergraphs? Yeah? Okay, what is the number of such intersecting family? So is it 2 to the n minus 1 choose k minus 1, 1 plus little 1 with a lower order term? Okay, I forgot to mention here what they prove is for any n at least 2k. Okay, when n is smaller than 2k, every 2k sets they overlap. So is this true? So this is the work of Pollock and me and Das, Delcourt, and Marion. So we show that yes, this is true. Yes, as long as n is at least 2k plus 1. Okay, so now you want to say, well, why 2k plus 1? Why not 2k? Or for 2k is not true. You get much bigger. Why? Okay. So just very quickly, I want to tell you 2k is not true. If n equal to 2k, what happens is, if this is the ground set n, you can always split it into 2k sets. One is a complement of another, right? N equal to 2k. Then for k set A and its complement A bar, you can always choose A or A bar, or you don't choose anything. So you have 3 choices for each such guy. So you can generate 3 to the n choose k over 2. You have this many pairs, right? And when n equal to 2k, n choose k over 2 happens to be n minus 1 choose k minus 1. Which means this bound n is at least 2k plus 1 is optimal. When n equals to 2k, it's exponentially more than 2 to the n minus 1 choose k minus 1. Meaning intersecting families. Okay? Yeah, you can only choose one, right? Because otherwise you get a disjoint pair. Yeah. Okay, so for question 2, we also answer. I will not get into detail. Basically, we show that for almost optimal bound, we show that almost all intersecting family, it's a subfamily of this kind. They all contain the special guy. So you know precisely how they look like. Okay? So, right. So there are several such problems also in number theory. For example, Cameron and Ehrlich, they have a conjecture about some free sets. So now if we consider a subset of first n integers, it's called sum free if it does not have a solution to this equation. If no solution to this, okay? Sometimes such x, y, z, x, y, they don't have to be distinct. So such a triple, sometimes we call sure triple. And yeah, so in other words, A is sum free if A plus A is disjoint from A. Okay, this means the set generated by taking the sum of 2 elements in A. In other words, this is what it means. So, an easy observation, the maximum size of a sum free set of n is n over 2. Well, there's some floors and ceilings. I will skip this floors and ceilings. Suppose, yeah. So there are 2 extremal structure. One is you can take all the odd integers in the first n, yeah, odd plus odd is even. Another is you can take the second half of the interval, simply because when you add 2 numbers that is at least n over 2, you jump out of this interval. Yeah? So it's sum free. So, or I call I2. I2 means, so I1, I2, this second half of the interval. It's very easy to prove this. So then, by taking any subset of one of these 2, you generate many sum free sets. You get 2 to the n over 2. Yeah. So the contents of this conjecture is that the number of sum free sets of n is big O of 2 to the n over 2. Okay? So in the late 80s, Noga Along and also Andrew Granville, they have some weaker result showing that the number of sum free sets is 2 to the n over 2 plus little o n. Okay? So, but you see, this is error term in the power, so it's weak. We don't know. This is asymptotic count here. So it was not for another decade. It was finally solved by Ben Green and independently Shapozenko. I think this is 04. This is 89 and 90s. Independent work. So what did they prove? They actually prove in a stronger sense that there exists Ci, I 0 and 1, such that the number of sum free sets of n equals to Ci plus 1 little o1 times 2 to the n over 2, where I has the same parity as n. So when n is odd or even, this constant is slightly different. This is reflected by the extremal structure here. I was a little bit sloppy here. When n is the odd or even, the extremal structure is slightly different. There's a shifty set. Anyway, so they proved the stronger one. Yeah. Right. Now, if you remember this triangle family and maximal triangle free graph, there's a similar thing here, asked also by Cameron Erdős. So Cameron Erdős asked, is the family of maximal sum free sets exponentially smaller? Yeah? Is it true that it's 2 to the n over 2 minus some epsilon n for some absolute constant epsilon? Yeah? So this question whoa, what did I do? Oh, okay, it's this eraser. Right. Okay. So is it exponentially smaller? It was not so clear. Then Thomas Wuchak and Schoen, L comes first. Yeah. So I think this is 01. They proved that this is, yes. So this is the first attempt to answer question 1 and question 2 that I said in the general setting, right? To estimate, so the first step is it significantly smaller? So they say yes. So they give an upper bound that's at most 2 to the n over 2 minus some very small constants, but absolute constant. Yeah. Okay. So what is the lower bound? Well, the lower bound is 2 to the n over 4. Okay. I can put some constant here, but let's just say 2 to the n over 4. So there's still this exponential gap. Is it closer to 1/2 or closer to 1/4 in the power? So how do you get this lower bound? So there are two types of constructions. I will mention one. I will just mention one. So what do? We want to generate maximal sum free set. What we do is, suppose we will generate A. We want to generate exponentially many AI, where each AI is maximal sum free set. What we do is, suppose for simplicity n is even, we always put n in every set. Every set will contain n. After you put n in A in every set, this n kind of nicely pair up all the odd integers. Okay? What do I mean by that? Meaning that now since n is in AI and AI has to be sum free, each one of these pair of odds, you can only pick one. Yeah, at most one. Then we're going to pick exactly one of such pair. Okay? So the number of such pair is n over 4 pairs. N over 2 odds give you n over 4 pairs, and you have two choices for each pair. That's how you get 2 to the n over 4. And As noticed earlier, some of these sum-free set might not be maximal. You might have to add some even numbers, but they are distinct. But once you extend it to maximal, they are distinguished by looking at the intersection and odd numbers. Okay. So this is how you get that. And Wolfowitz improved this upper bound to 2 to the 3n over a plus little o n. So he shows that at least it's not closer to 1/2. Okay, it's 3/4. So what we do, this is in two paper. In the first paper, we answer the first question. For question 1, we show that, in fact, we determine the constant in the power. It should be 1/4. Okay. Now the harder question, for the second question in the second paper, we prove that the typical structure. We show that almost all, they look something, a subset like this, and another construction. So there are two very different kind of construction. We show that the typical structure look like something like one of these two constructions. In particular, a corollary of the typical structure gives you a precise count, showing that there are constants. There are 3 constants such that the number of maximal sum-free sets equal to ci plus little o1 times 2 to the n over 4, where I is a modular of n mod 4. Okay? Because in the second construction, it matters the residue of n mod 4. So this is what we prove. Yes. All right. So the counting problems today is so-called, another counting problem is Ehrlich-Rothschild problem. What is it? So for a graph, Ehrlich-Rothschild problem. So, right. Now, we will consider, so given the graph G, okay, given the graph G, we will consider the edge coloring. Let's start with two edge coloring, with 2 colors. Yeah, two edge coloring. Yeah, 2 edge coloring of G. You color the edges. But there's we put some restriction on the coloring. We require that the coloring is triangle free, meaning that there's no monochromatic triangle, say. Yeah. So triangle free coloring. Okay. In other words, if you look at each color class, it does not contain triangle. Okay. Then we can define this parameter f of G2. Okay, 2 means 2 colors. Let me put another argument here. K3, meaning that the coloring is triangle free. 2 coloring of the edges, triangle free in each color class. This counts the number of such coloring. Okay. Right. So let's try to understand this parameter. By Ramsey, we know that if G contains a large clique, no such coloring exists. In particular, by large, I mean 6. Yeah. If you have a K6, then no matter how you color it, you'll get a monochromatic triangle with 2 colors. So first of all, we know that we have to pick. It's only interesting to consider G that does not have a large clique. Second of all, if G itself is triangle free, then we are safe. No matter how you edge color it, there's no triangle in any color class. So the parameter they're interested in is, let me define f of n, 2k3. So they want to look which n vertex graph maximize the number of triangle free colorings. Okay, so this is the max of f g2k3, where the number of G has n vertices. So you maximize over all n vertex graph. Is that clear, the definition? Yeah. Okay, so because of this observation, we have a trivial lower bound. So what is trivial lower bound? Let's grab the maximum size triangle free graph. There's a two-round graph on two parts. And you can calculate whichever way you want. So you get 2 to the n squared over 4. Okay, so this parameter, this is a trivial lower bound. In particular, Ehrlich and Rothschild, they conjectured that this trivial lower bound should be tight. It should be exactly 2 to the n squared over 4. Okay, so this is conjecture by them. And this is proven by Euster in the 90s. So what did he do? He showed that yes, this is true. Okay, and furthermore, he himself conjectured that if you, instead of triangle free coloring, if you look at any clique, larger clique, the kt plus 1, then this trivial lower bound, instead of two-round graph on two parts, you take t is not a good letter. Let's say k. You take two-round this is the number of edges in k part two-round graph. Yeah, you take 2 to the t sub k of n instead. So he conjectured that this phenomenon should continue when you forbid a larger clique. This is this was proved. So indeed, along Bala, Kivash, and Sudakov 04.
So is this the asymptotic? I'm talking about asymptotic upper bound?
This is exact. So this is equality, yes, without error term. So basically, yeah. So I will write this down. So they proved that Fn for R, okay, kk plus 1, where R, they proved not just for 2 colors, but also 3 colors. You can use 3 colors on the edges. They proved that for R equal to 2 and 3, this equals to R to the t sub k of n. And furthermore, the two-round graph on k parts is the unique maximizer. Okay. This is what you're asking, yeah? Yeah. So they show that, yeah, this is exact results. Right. So this is a very difficult problem, actually. So let me tell you why. Because when the number of colors gets bigger, this trivial lower bound is not true anymore. Some Renzi flavor kicks in. Okay. What do I mean by that? So let's consider, say, 4 colors triangle. Okay. 4 colors triangle. This trivial lower bound will give you 4 to the n squared over 4. But this is not true. This is exponentially smaller than the actual value. So this was proved. So for larger color, very little is known. Just these 2 cases proved by Pickerkel and Yuma. I think this is 2014 or 15. Yeah. So they proved that this is uniquely maximized by 4-part two-round graph. And if you forbid 4 color K4 is T9. So for 4 colors, only these two cases are known. So the situation gets really bad. The first open problem, if you're interested, even 5-color triangle we don't know. Okay? Meaning that if you 5-edge color the n-vertex graph, which graph maximizes the number of triangle-free colorings? And by we don't know, I don't mean it exact. Even with the error term in the power, even the very weak asymptotic, even like say some constant to the some cn squared plus little o n squared. This is not known. We don't know how it is like. Okay? So this is quite hard. So what we do in our paper with Mary and Catherine is the Erdős-Rothschild problem, but in a sum-free setting. Okay? This is rather natural because we have already seen this nice parallel of triangles and sum-free set. Yeah? Let me just give you a list all we've seen so far. You've seen triangles in graphs and sum-free sets. In the arithmetic setting, what we have seen so far? Well, this nice parallel. Well, I didn't tell you the Mantel's bound, but then Mantel proved the maximum size of a triangle-free graph. Then we also know this maximum size of a sum-free set n over 2. Okay. And then after there's a famous Rusha-Semeredy triangle removal lemma, saying that if you don't have many triangles, then you can remove a very tiny portion of the edges to make it genuinely triangle-free. Then there's also a sum-free triangle removal lemma implied by this lemma of this abelian group. Well, actually, it was proved generalized for all group by Dan Krall and Sarah and Vanna. So this is Green, Ben Green, Krall, Sarah, and Vanna. So there's a group removal lemma which implies that if you have a set that is almost sum-free, then you can remove little o n elements from this set to make it actually sum-free. And we've seen this Erdős, Kleiman, and Rothschild of counting the number of sum-free sets. Yeah, triangle-free graphs and their typical structure. Yeah, and their typical structure. And the parallel we've also seen is the result of Green and Shapozenko, where they count the number of sum-free sets is 2 to the n over 2. Okay. So, and there's a maximal version that we have seen. So now it's this Erdős-Rothschild. We consider here. This is what we do here. Okay? Let me give you the definition. I say F given the subset of n, FAR, what is it? This is the number of R sum-free coloring of A. What does it mean, R sum-free coloring? So that means I color A, elements of A by R colors such that each color class is sum-free. Yeah? Similar to this Erdős-Rothschild problem where each color class is triangle-free. Now I require each color class is sum-free. So surprisingly, well, not so surprised actually, not a big prize. So here I mentioned that for 5 colors, triangle is somehow still out of reach, but we can prove asymptotically for 5 color sum-free set. Intuitively, why we can do this? Because the maximum size of a sum-free set has very rigid structure, while in graphs there's this huge symmetry. You can rotate this T2 bipartite graph. So this is the intuition. So okay, so what did we prove? Let me finish the definition. So we define Fn of R. We maximize such coloring over all subset of n. Okay? So a trivial lower bound is, as we had before, if A itself is sum-free, then it's easy. We can color it whichever way we want. So the trivial lower bound, again, low is at least R to the n over 2. Yeah, R to the n over 2. We grab we let A to be maximum size sum free set. So what we prove is the following. We solve the 2-color case exactly, and for 3 to 5 colors we prove it asymptotically. So this is so we show that okay, so we prove that if you have 2 colors, then the best you can do is to grab a maximum size sum free set. You cannot do better. Any other set has strictly less 2-color sum free coloring with 2 colors. Okay? For 3 to 5 colors, okay, let me just write it separately maybe. So for 3 colors we get basically an asymptotic version. So this lower bound is still true. Where is it? Yeah. So for 2-3 colors, this lower bound is true. It's tight in the sense, yeah. But already for 2-color exact result took a while, so we didn't pursue for the exact version for 3-color. And for 4 and 5, what we prove is f of nr is r times r squared over 4 n over 4. Okay, something like this. Right, so if you compute, this is exponentially bigger than 4 to the n over 2, say, or 5 to the n over 2, if you take the corresponding r. Okay, so how do you get this lower bound? Okay, so basically, when the number of colors is at least 4, it's not optimal to take a maximum sum free set. So what you do is, remember this 2 extremal set, which is the set of odd numbers and the second half interval. We're going to let A to be the union of these 2. Okay, odd and the union. So these are the odd. This is the second half interval. So what we do is, I would like to look at it this way. So let me tell you what I mean by this. Suppose r equal to 4. Okay, so this is my A. I have the second half and the odd from the first half. All the elements from the second half. So for the odd numbers, I can color it. I always give color 1 or 2. For the elements in the second half, I always give color 3 and 4. So in other words, odd elements in the second half can be colored whichever way we want. Yeah. If you color it this way, look, every color class is sum free, so we are safe. Does it make sense? So if you count, if you do the counting, this generates roughly this much coloring, and this is exponentially better than r to the n over 2. Okay, and this set obviously is not sum free. It contains maximum order of magnitude number of sum free sets. So this is what we prove. So it's tempting to say, is it true that this will continue? At the beginning we think that maybe this is true. What do I mean? For a larger R, is it true that the maximum is achieved by this set? Meaning that we will put R over 2 colors here and R over 2 colors for the I2, yeah? And turns out this is not the case. You can do exponentially better. So in general, not true. In general, this problem is quite hard. Why? If you consider this set, I2 union O, union, I call this class P. What is P? P is all the elements that is 1, 4, mod 5. Okay? You take all the numbers that that has residue 1 or 4 mod 5. This is a sum free set, because if you 1 or 4 mod 5, if you sum up 2, it's always 2 or 3. Yeah.
0.
Oh, 0. Yes. 2 or 3 or 0. Yes. So this P is also a sum free set. So what you can do is you have this, you can put R, a third of a color here, a third of color for this, a third of color for that. And if you compute it for large R, this guy does strictly better. So in general, this problem, we don't see a way to do it. So it would be nice to see a clean way to say, describe the extremal set, but we don't know. Yeah. So I have 2 minutes. Let me just roughly says how we can do this. So very roughly, what we do is, first of all, we use the main tool is a container lemma of Ben Green on these abelian groups, which roughly says you can use you can use a small collection of subset of n, such that very roughly, you can use a very small collection of subset of n, such that every sum free set that you get is a subset of one of these members. Okay, meaning container. And another tool we use is a stability result of Schoch, Tompkin, Dejouy, and there's another one. Sorry, and Freeman, of course. Dejouy, Freeman, Schoch, and Tompkin, which tell you the structure of a sum free set that is close to maximum size. So what we do is very roughly, this original problem of counting f, we use the container theorem. If you've done, so some of you have done some counting problems, so we use container to translate it to a linear optimization. We can translate it into a problem that can it's a linear optimization problem, linear program. And the constraint of this linear program we can obtain by the structure we get from the stability and also the theorem. So here we will use the stability to look at the structure. From the structure we will get more constraints to solve this problem. And this problem will give you an asymptotic solution of f, very roughly. But if you're interested, I can tell you more details. I think I'll stop here. Yeah.